Cool. Well, hello everyone. I'm going to try and give a quick and whirlwind introduction to the world of music theory. I have given a similar talk to this before with the code written in Ruby, but I've now do a lot more Ember, so I've rewritten the code into JavaScript. Is there much Ember in this talk? Well, not really in the talk, but I am going to give a quick demo afterwards of an Ember app that's built on some of the code I'm going to show you. So, first thing I want to ask is, does anyone here know any music theory already? A few people know a little bit. So, not many people said put their hand up, but I'd really ask, like, are you sure you don't know any music theory? Because it's actually a lot simpler than you may have been led to believe. First off, you've got vibrations, which are what sound is made of. Then you've got vibrations at specific frequencies, which make notes. When you choose certain specific groupings of those notes, you get scales. And when you play specific notes together, then you get chords. And then you play some chords in order, and you get songs. And I would argue that most of you probably knew that, and that's kind of really all there is to it. The rest of it's just in the details. The reason I kind of put together this talk is because I really found music a hard thing to learn. I've played guitar for probably 20 years now. I'm not very good at it still. I'm quite good at playing the notes and making my hands move in the right ways, but I don't really kind of feel the music, and I think that music is taught a lot in a way that only really benefits natural musicians. And if you did music lessons in school, you might have been sort of expected to just know, what notes are playing next, this is a third, this is an interval, and you might kind of, if you didn't get it already, there wasn't really anything given to kind of explain why and how. So I decided to implement it from scratch in code, because as Jeff Hawkins said, if you can't build it, you don't understand it. So I wanted to try and kind of build it from scratch. So to do that, did a bit of research and started reading about the basics. I'm going to start off with the frequency of 440 hertz. This means 440 cycles per second. So if you can imagine a sine wave that repeats itself 440 times every second, that is what this would look like, and this is an A. It's called A4 because it comes after A3 and before A5. It's an ISO standard apparently, and this is in maths what you kind of call an axiom, so it just kind of is. Like, why is it that? Well, because someone decided it was that a while ago. It looks like that in musical notation, and I haven't actually checked if my sound is on. Sounds like that. So, how would we generate something like that in code? Well, if you wanted to start from complete scratch, which I did, you would probably build something that looks a bit like this. This is a incredibly basic sampler, and what this does is it generates samples. So if you look at something called like the WAV format, which is, you might have seen WAV format files, it's basically a music file without any compression. I guess the comparison with image formats might be something like a, TIFF file without compression. It's just like each frame is a number one after the other, and then it's not compressed like an MP3 would be. It's just a series of numbers. So if you wanted to build a note, you'd pass in a frequency, so you could pass in 440 hertz to build that A. You'd pass in a sample rate, and the sample rate is just some arbitrary number. It has to be double the highest frequency you want to represent because of something called the Nyquist theorem. And so because humans can hear up to about 20,000 hertz, if you've got good hearing and you're also quite young, you would probably choose something like 44,100 as your sample rate, which happens to be what CDs use. Then you pass in a duration, so you might want 1 second. once you've got that, there's really not that much code here. You'd figure out how many total frames you want, and a frame is just a floating point number. It's between, I think in WAV it's between -1 and 1. Yeah, between -1 and 1. So you'd figure out how many frames you want, that's how many numbers you want to generate. You figure out the cycles per frame. So each frame, if you're playing this note, how many iterations of that sine wave you're going to go through. And that's always going to be less than 0.5 if you've chosen your sample rate correctly. So you've got this sine wave that goes up and down like that, and in this frame you want to represent a tiny chunk of it. So then you do some maths with pi to basically work out the increment, which is how far along the x-axis of that sine wave you want to increment. And you then take the sine of that phase, which starting at 0, starting at the 0 on the y-axis, you take the sine of that to get how high up you want to go on this sine wave, and you just push it into your array and then increase by the increment again. So that's all well and good, but this is not particularly practical. I'm sure there is a way to take these floating point numbers and then generate a WAV data header, put this in the end of the WAV data that you've got, and play it in the browser. It would be much easier actually in Node.js, but it's also kind of stupid because the browser actually has really nice APIs for doing this already. The Web Audio API lets you just create an oscillator and tell it the frequency, tell it to start oscillating, and you give it a destination, which is going to be the speakers in this case. And you just start it and then stop it 1,000 milliseconds later. So if you're doing this in the browser, the Web Audio API is probably what you want to use for this. It sounds a lot like that. So okay, we've got one note. It sounds a bit basic, it sounds very computery because it is. There's none of the timbre and the interesting kind of qualities you would get from a real instrument, but that's kind of not the point. And what I'm trying to do, I kind of want to understand the music theory rather than the music practice of the instruments. So let's start off with octaves. In music theory, notes repeat every octave. What repeating means is that the frequency is doubled. Human ears, for some reason, are very good at hearing simple ratios between frequencies. So they're very good at hearing double. You can hear one frequency and you hear double that. It sounds like the same note for some reason. And the other intervals are like that. You can hear kind of 3 times the note, 4 times the note. For some reason your ears are good at recognizing that and consider it to be music. So if you want to double the frequency of a note, if we started off at 440, you could double that and get 880, or you could halve it and get 220. So if you had 3 octaves of A, if we had our play note function that we implemented earlier, we could just play the one below, the one we just played, and the one higher. So those are all 3 octaves of A. That's a bit boring, but we can build on that. We want to build some tones and semitones. So semitones are the smallest interval common in Western music. You can get kind of microtonal music, and actually in Western music, if you hear bending in guitar solos a lot, you're hearing kind of microtones, but they tend to kind of start and end somewhere on a semitone. So it's quite unusual for you to actually play music that ends on a microtone. I am mostly talking about kind of conventional Western music here. There are a lot of other traditions that are quite different to this. A semitone is 1 fret on a guitar or adjacent note on a piano, including the black keys. And so what's a tone? Well, it's just 2 semitones. So if you want to move semitones, so let's say we've got our 440 Hertz A and we want to find out what the next note is, 1 semitone up, we need to do a bit of maths. There are 12 semitones in an octave, and to move up 1 semitone, because we're kind of doubling here all the way, we want to multiply by a ratio. We can't just add a frequency. And we want to multiply it by a ratio which we can call R. And we need to figure out what R is. Well, since we know to move up 12 semitones, which is an octave, we have to double the pitch. We know that this ratio we need to the power of 12 is 2, because if you multiply by this ratio 12 times, you've doubled, so you've got it to equal 2. So then you can work it out by taking the 12th root of 2, which just happens to be 1.059 something. And so to move from the next semitone up from A, we just multiply 440 by the 12th root of 2. We get the next frequency, which is 466 point something. So once we know that, it's quite easy to take an A. Let's take the lower A, because the 440 Hz A is actually quite high, and we don't want to go up and start hurting our ears when we start playing this stuff. We want to, 12 times, play the note, and then just multiply by the 12th root of 2. Do that 12 times, and we can get all of the notes really simply. So that's all the notes. That's pretty good. Now we can start building stuff with the notes. So one thing you're probably going to build with notes first off is going to be a scale. And that was a scale, what I just played you. That's called the chromatic scale. What that means is just all the notes. But scales are interesting because they're patterns. So the one we heard doesn't sound particularly musical, I guess. I mean, it sounds, you can hear that it's notes, but it's kind of sounds a bit like a joke, maybe one of those like kazoos that you'd play or something, or some kind of like joke kind of music gag in a film or something. Most of the scales that you hear in music, in Western music, have 7 notes, not 12. 7 notes, 8 notes. I mean, they have 7 different notes, but if you hear one, you'll usually hear the octave played as well, so that you actually hear 8 tones, but only 7 unique ones. So let's start with the major scale, which is the most common scale. The most common? I don't know. The major scale is the first scale you'll probably learn in any music theory lesson. We just take 7 specific notes and take them in a pattern, which is tone, tone, semitone, tone, 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 semitone. And really, like, that's just 2, 2, 1, 2, 2, 2, 1. So that's how many semitones you're jumping each time. Supposedly it sounds kind of happy. So to generate that, I'm just going to assign some constants. Tone equals 2 and semitone equals 1. Put the pattern in an array, and then each time we jump this time, we're multiplying by the 12th root of 2, but we're multiplying it either once, so I'm raising to the power of step, which is either going to be 1 or 2, and if it's 1, it has no effect, but if it's 2, it's the same as multiplying by the 12th root of 2 2 times, so we're jumping 2 steps. And that's the major scale, which is, you might recognise from, I guess, The Sound of Music, where they sing do, re, mi, fa, sol, la, ti, di. I can't sing, by the way, but they do. And you can generate other scales. So the minor scale is kind of like the more sad scale, which supposedly sounds a bit more sad. So we're going to take a different 7 specific notes. The pattern is going to be slightly different: tone, semitone, tone, tone, semitone, tone, tone. And supposedly it sounds sad. And the code for doing this is identical, with the exception that we just changed the pattern that we're iterating through. So yeah, sounds a bit sadder, I guess. So I'm just going to introduce a quick abstraction. This is nothing really new here. Making a function to increase the frequency by a number of semitones, which is just the code we had before, and a function to get the frequencies from a list of semitone jumps like we just had. So this is basically just a nice way of reusing the code on the previous screen, so that the code doesn't grow big in my next examples. Nothing new there. Now I'm going to introduce modes. So a mode is just a scale, but the idea is that there are 7 different modes, and the 2 scales that I just showed you are 2 modes, and there are 5 different ones. So modes are just rotations of the major scale. So the major scale, the first one I showed, is the Ionian mode, and to get the next mode, you take one interval off the top of the end of the array, which is going to be S or T, bring it to the beginning of the array, and that's your next mode. And so both of those scales we showed already are rotations of each other, but they're not next to each other. So if you want to generate all the modes, you would start off by generating the major scale, and then you just push onto the beginning of the current mode the last item. You push onto the end of the current mode the first item, so you're just rotating the array. Rotate it once, play it through, rotate it once, play it through. And that sounds like this. So those are all the modes, and with those you can build pretty much anything. Thirds are jumps on a scale, so basically you would take one of those modes that you've generated, and instead of going up one step at a time, you go up 2 steps at a time. So they can be major or minor, and a major third is where you go up 2 tones, so it means you're adding 4 semitones. A minor means you're going up 3 tones, which means you're jumping a tone and a semitone. In Western music, there aren't any thirds that are 2 semitones, because there's no patterns that are 2 semitones next to each other, but there can be in other types of music. So you just map out a scale and choose one note from it, and then on that scale, either a major third or a minor third will be a possible move. That's what's available. You can just look and see, oh, it's 3's available, or 4's available, 4 semitones. So another way to look at it is you're just skipping notes in the scale pattern. So I made this function circular array just to make it so that if you access an array and you try and access an element that's greater than the length of the array, you won't get nil. It will just take the modulus of the index and treat it kind of as if it was an infinitely repeating array when it's not. I'm going to go up in steps of 2 this time instead of steps of 1. We get step 1 and step 2, which is either going to be tone and semitone, or tone and tone, which is going to be 1 and 2 or 2 and 2, and then we jump up that instead of jumping up 1 step at a time, and that sounds a lot like this. So that was thirds, and then let's move on to chords. Basically, to make a chord, you play several thirds in a scale, like we just did, but you play them together at the same time. So if we take the code that we had a minute ago, which is very similar, the only difference is I've just removed the await before play note, so that it plays them at the same time instead of playing them one after the other. I've got a nice chord. Sounds kind of very choral. The reason for that is that these are perfect sine waves. So a lot of the quality of an instrument comes from the imperfections in the waveforms that it puts out. If you take like a recording of like a guitar and you chop off the first like 200 milliseconds, it will sound a lot like that. Your brain kind of imputes a lot of the sound of an instrument from like the first few milliseconds when the notes start. And lots of instruments with the first kind of few hundred milliseconds chopped off sound very similar. So, chord scales. Chord scales are very much like modes. So you basically take all the modes and you generate thirds from those modes like we just did, and then you play them together. So you can make different chords from a scale. Chord you make starting from the first note is called the 1 chord, I chord, Roman numerals. And they will automatically be major or minor, and that means that they will either have a major chord, a major interval first, major third first, or a minor third first, and that's just what fits into the scale pattern that you generated. And so each mode has a chord that you make from it by moving up in thirds. So if you take those modes that you generated earlier, you can fit a chord by starting on the first note and then figuring out, oh, is it a major or a minor interval next. In code, this looks like this. So this is kind of looking like a combination of the things that we did earlier. So I'm taking the major scale and iterating through one at a time. I'm getting the first third, which is the first two semitones the first two intervals added together, so that's going to be tone and semitone or tone and tone again. Second thing, which is the second third, which is going to be tone and semitone or tone and tone again, and generating the frequencies for those, and then playing them all at the same time. I'm using rsvp.all to play those three notes at the same time and then await those to finish playing so that we can play one chord, then another chord, and then another chord. And then again, we're just rotating the mode at the end by taking the first element and putting it on the end of the array. So that's basically all of the chords that you can play. So when someone says, I'm going to play a song in C major, that means that you could run this algorithm. You'd pass in as the start frequency the frequency of some C major, low or high or whatever. It would generate these chords, and it means that you can use any one of these chords and it will sound nice in C major. And when they play a song in C major, they're probably going to say, I'll start on the first chord and the second chord. So that's called a chord progression. So common one is 1, 4, 5. So they generate those chords. I mean, if you're a musician, you'd probably like do this in your head, or you'd know the patterns. So you'd know all of those chords like from the chord scale I just played, and you'd say like, oh, 1, 4, 5 in C major. So I start in C major, and I play the next one over here, and I play the next one over here, and that's a 1, 4, 5 song. And then I've got some other chords in that chord scale I can kind of drop in to make it sound good, make it sound not repetitive. 1, 4, 5 is really common though. So yeah, basically one or more. Once you've generated a chord progression or made up a chord progression, just take one or more of them, and you've got a song. So yeah, when music is decimalized, it really must be made zero indexed. It's kind of annoying to program stuff like this because you end up like assigning Roman numerals to numbers that aren't really them. But anyway, ignoring that fudge, you can just iterate through these chords. So 1, 4, 5, and then back to 1 again. And just await playing the chord. Sounds a lot like this. And if that sounds familiar, probably should, because it's like every song ever. It's like millions and millions and millions of songs. Like, I mean, there are other chord progressions that like people use to like make songs that don't make any money, but if you want to like make a pop hit that everyone loves, like you really should just use this chord progression, and like think of some nice words to say over it. So I guess the point of this whole thing is like, you know, do I think I'm going to write good music in code? Like, probably not. I mean, there is great apps to write music that are kind of a bit technical, like MIDI apps. You get a MIDI keyboard, and there's kind of apps that let you, I mean, there are specific apps that are designed to have their own kind of programming language for music, and you could probably use those to write good music. There are like music apps that you can use to make good music, but this is really an exercise in understanding rather than an exercise in actually making something nice. And it's also kind of an exercise in abstraction. We started off from just a number. We started off from the number 440, and with nothing else apart from some browser APIs, we built pretty much the whole of music theory that most musicians will use. I mean, you get musicians that know that there is quite a lot more to this, but if you know only the things I've given you in this talk, you know, you could pretty much write most of the music that you likely listen to, unless you listen to some really esoteric jazz or like math rock or something. So, you know, you can abstract this. I mean, this is... that kind of sounds like something out of Zelda, I think. It's like using the basic building blocks that we've just done, and you can see that it's actually quite simple to write something that sounds actually musical from building blocks that don't. I guess my point is that if you come to music and you've never really done it before, like, this looks beautiful. I mean, like, it just looks beautiful, but I mean, I can't read it. I'm sure lots of musicians could, and sight reading is a skill all on its own. But my point is that this really, as a programmer, when you see that, you should be thinking that those are like the notes that you're playing in order. That previous notation is very hard to actually extract the meaning from that. Like, were they thinking, oh, I want to play this chord and this chord? No, they're just writing down the individual notes that you play, and then you have to figure out the abstraction that they were thinking in. So I guess that's kind of my point, really. You can break this down into quite simple steps, and there's actually, I've repeated a lot of code there. There's probably like 50 lines of code altogether in this whole talk that are like remotely unique, and it's not actually that complicated at all. I got some links here. I'll probably tweet these slides to Pablo, if you're up for tweeting them out, so that people can click on these rather than trying to write them down. But yeah, that's everything. Thanks for listening.